Okay, we're rolling. So we got this fxy equals x plus 1 is that plane, right? And that's our surface. Could be a multivariable rate function, like we've talked about. And then do you see that the blue regions are showing the exact same region R? Do you see that? That's important that you see that. In both cases, I'm showing the exact same set of points. X goes from 0 to 4, and Y goes from 1 to 3. If this is X coming out this way, oh no. Okay, so we want to. So this region defines a solid laterally, and then the function gives us the top of it, and the xy plane the bottom. So the xy plane is the bottom. The function f is the top, and r defines the lateral surface. And that gives us a solid. So what does that solid look like then? So then the region, just that outline of that region, you just extend it vertically, and that defines, like I said, the lateral surface of this. The sides, right? The sides. We'll just take the boundary of R and just extend it up and down, and you get the sides. Okay. Okay, can you see, does that make sense, what I've drawn there? Okay, so find the volume of that. So first of all, by geometry. So use whatever means you can. How much three-dimensional space is taken up by that solid, right? So find the volume. Ready? That's your task. You can work together. You're either making progress or you're getting help. One of those two. Two, right? This is 4, and this is 1. So the bottom rectangle is? And so what is this? From here to here is that 4? This is 5 and 1, right? So this is 4 and 2. So V2 is 4 times 2 times 4 again, times 1/2. Did you get 24? If you got 24, you did it right. Any questions on that? I added up the shoebox plus the wedge on top, the cheese, this wedge of cheese. Any questions on that? Okay, so now what about calculus? So calculus would be what? Summing up little rectangular columns, right? Summing up little rectangular columns whose heights are, what are the heights of those rectangular columns? What's that? Right, x plus 1, f of xy, are the heights. And then the little areas of the bases of those rectangular columns? Dx dy, right? Right, so that's the volume of one rectangular stick, which could also be a little bit of the quantity for which f is the rate, right? So if the f is the multivariable rate, per change in x, per change in y, and multiply by a little change in x, a little change in y, you get a little bit of the quantity. And so you can either think of this as accumulating bits of the quantity calculated by the rate f, or as summing up volumes of these very skinny, tall, rectangular solids. So no, because these is a rectangular region, it doesn't matter. But only because it's a rectangular region, you can just switch it. We'll talk more about that. Okay, so let's do this. So we got fxy is x plus 1. And we're going to hold y fixed, and x is going to go from what to what? 0 to 4. And then y goes from 1 to 3. Okay, so we do this, we evaluate these double integrals the same way we evaluate partial derivatives. It's like partial antiderivative, right? So when we do this, so we've got, with respect to x first, what happens to y when we're doing it with respect to x? We hold it steady, right? We hold it constant, and we look at accumulating across, for changing x for a constant y, right? We're holding y, for instance, it's like we're holding y as any typical y, and then we're going to accumulate across for x, like this. Okay, so then we got from 1 to 3, antiderivative, easy, right? X squared over 2 plus x from 0 to 4 dy. And what is that? 16, 8 plus is 12, so we integrate from 1 to 3, 12. And that's 24. Okay, if we were to do x plus 1, if we were to do dy first, so let's just show that you get the same thing if you do dy first. So if you do y first, it's going to be what now from 1 to 3. And so if we hold, now we're holding x constant as we integrate with respect to y first. So what's the antiderivative of x plus 1 if x is a constant? xy plus y, and we evaluate that from 1 to 3. And so that is going to be 3 substitutes in for what now? Y's, right? So it's going to be 3x plus 3 minus parentheses, x plus 1. Make sure you're subtracting this whole thing with 1 plugged in, so you need parentheses. And so that gives us integral from 0 to 4 of 2x plus 4 plus 2. I did what I said not to do. So that's x squared plus 2x from 0 to 4. 24. So you work from the inside out. You work from the inside out. You hold your outside variable, you hold it as a constant, and do antiderivative with respect to that inside variable. But then everything else is the same as all the antiderivative and fundamental theorem that you've done before. Okay, so do double integrals, we asked this question last time. Do double integrals always give you volume? Do they always give you volume? No, why not?
Sometimes it could be like a rate or
Okay, so when we're in geometry mode. So when we're in geometry mode, we're looking at R3, okay? We're looking at R3. We've got the surface, and we're strictly in geometry mode. We're not in rate of change accumulation mode. In geometry mode, will we always get a volume? Alex?
if the function is 1 area.
That's okay, but that's still a volume. Yeah, so we could use it to find area, that's true. But we still are getting a volume with height 1. Yeah.
It's volume underneath the surface, but it doesn't mean that your answer is in volume.
Well, what do you mean?
So like, you're finding the volume on the surface, but depending on what your units of the actual problem might be, your answer could be anything.
So now you're going back to accumulation and rate mode. Is that what you're saying? Yeah, so we're not in accumulation and rate mode. So that's true. That's absolutely true. But just strictly in geometry mode in R3, will this be units, always be a volume of units cubed where the units are the axis scale?
Yes.
No. Why not? But thank you. So why not? Yeah, Christian.
Would it be because the function could have a negative?
If the function carves out negative solids underneath, and we're integrating f, then these values could be negative. And what would that mean for the double integral? You'll get that accumulation of volume will have a negative contribution to the total. So you won't always get volume, but instead, if sometimes it's above and sometimes it's below, what could we say? We're going to get double integrals in geometry mode give. So if we get a positive contribution of volume when the surface is above the xy plane, but then when the surface is below the xy plane, those give a negative contribution to the overall integral, double integral. Then what is it really giving us? Yeah.
Change in volume?
Yeah, like net volume or difference in volumes. Net volume or difference of volumes, that means the same thing. It means any volume that's above is added, and then any volume that's below gets subtracted. That's for difference. Difference of volumes, or net volume. If the surface always has positive z values, then yes, you get volume. But if the surface ever dips below the xy plane, it carves out volumes that get subtracted. Right? Volumes that have a negative contribution to the overall value. So then it's not volume anymore. It's like the difference of volumes. Does that make sense? So this is really important. Don't miss it on the test. Double integrals. What do they give? They give volume if the surface is always in positive z-land, or difference of volumes if it ever goes underneath the xy plane and carves out a volume below. All right. So let's look at something else here. This one. So here's this surface. The gold surface is f of xy, 2 plus 0.6 cosine x sine y. And then the region is defined by functions b, t, and the x-axis. Sorry, y-axis, x equals 0. And x equals 2. So this defines R. You see that? 1/2 x is this bottom. That's B. The top is 4 minus 0.5x. And then starting at x equals 0 to x equals 2. And then again, you should be very confident that these two pink regions are exactly the same. I'm showing you exactly the same thing, right? Okay, so I want to find this is always positive. This function is always positive. So I want to find the volume defined on the top by f, the bottom by the xy plane, and laterally by the edge of the pink region, right? So the sides are defined by the edge of the pink region, extending up and down in the z direction. And then the top is defined by the surface, and the bottom is defined by the xy plane. So I can get that volume. It's truly volume because this is always positive, right? As a double integral over R of f. I could say dA, meaning either dx dy or dy dx. Okay, so last time we saw that with a rectangular region, you could just start with x, start with y, whatever you want. Well, here we have to think about it a little bit more. So let's start. We're going to start with y. Okay, so we're going to do double integral, and we're going to do dy dx first. And this is 2 plus 0.6 cosine x sine y. Okay, so we're doing, what are we doing first then? If I'm doing this, I'm doing what first? What variable first? Y comes first. So then how do we consider x as we're working on the y antiderivative? How do we consider x? Constant. So it's like kind of any typical x in here. And so then as we kind of fix x as any typical x from 0 to 2, then we're going to integrate, or we're going to accumulate, starting from the bottom to the top. So then what's the starting y value we're going to start at? So for this x, I could have drawn it here. It doesn't matter where I drew it, but given the value of x, I'm going to start at the bottom and go to the top like that. And so what's my starting value of y? Or in other words, what is going to be my lower limit of integration for y? Well, it's going to be whatever y value I get for this x that I chose. So what is that y value right there? 1/2 x. Do you see that? Or it's the value of the function at that x right there. So we think of it as fixed, but wherever we choose it is going to determine the y that we have. But it's always going to be 1/2 of the x that we chose. Does that make sense? So 1/2 x is the bottom. All right, and what's the top? 4 minus a half x. That's the top limit of integration. And then after we integrate our typical strip here from 1 half x to 4 minus 1 half x, then we'll be done and we'll be ready to integrate x. And x will go from what to what? So we're going to integrate up all these vertical strips starting at x equals 0, 2, 2. Right, so once I get my typical strip from 1 half x to 4 minus x, my first one that I'll do will be this one at x equals 0, and then I'll go across, and my last one will be at x equals 2. Okay, this is called, we're going to call this a type 1 double integral. A type 1 double integral will be dy, dA will be dy dx. And our mantra will be bottom to top, left to right. That's the mantra for, it's our cheer. It's our cheer for type 1 integrals. Bottom to top first, dy, right? We do dy first, so we find the bottom to top. And then once we're done with that, then we do the outside integral, that's dx. We go from left to right. That's a type 1 double integral. dy first, then dx. So we say bottom to top, left to right. Okay, and so let's write this awful thing out here. Let's see. Need some room. So let's do that. Here we go. Just do a little bit of the math here. So we hold x constant and do the antiderivative with respect to y. What will that be? So with respect to y, we get 2y plus 0.06 cosine x and negative cosine y. And then we're going to do that from 1 half x to 4 minus 1 half x. And then dx. You see it? Antiderivative with respect to y, keeping x as a constant. So here we go. Ready? So then we'll stop after this. But what we're going to plug in 4 minus 1 half x for y. And then plug in 1 half x for y and subtract. So we're going to have, here we go, 2 times 4 minus 1 half x plus 0.6 cosine x negative cosine of 4 minus 1 half x minus the whole thing with 1 half x plugged in. 2 times 1 half x. This is a little bit easier. Plus 0.6 cosine x negative cosine 1 half x. Lots of parentheses here. 2, 3. And now that whole expression, so one more set of parentheses. Dx. We'll stop. But normally then you would evaluate that with respect to x. And you get a number, and what would that number be? The volume where the bottom is the xy plane, the top is the surface, and the sides are defined by the edges of the region. extend it up and down. Questions on this example? Okay, so now what would... Did this make sense? Any questions before I erase it? Erase? Okay, so what would type 2 be then? So then we have a type 2 double integral. It's going to be dx dy, right? So it's going to be type 2. Will be the same function. Dx dy. So x goes from what to what? So pick an arbitrary y. X goes from 0 to 2, is that right? Yeah, so do you see this right hand, the right side is not always going to be x equals 2. Down here, if you choose your y down here, you get a different right-hand side. Same with up here. In fact, there's 3 different right-hand sides. So this is what x equals, this is 2y, and x equals 2. And what is this? X equals, do the math here, 2 times 4 minus y. Is that right? Yep. That comes from y equals 4 minus half x, solve for x. So what does it mean? If we want to do a type 2 double integral, what does it mean? We got to split it up into 3 different ones, right? So there's going to be, the first one is going to be when y goes from 0 to 1. And that's when x is going to go from, what, 0 to? Right, so when y goes from 0 to 1, x goes from 0 to 2y. And then when y goes from 1 to 3, what's our x doing? Going from 0 to 2. And when y goes from 3 to 4, 3 to 4, what is x doing? Goes from 0 to this, right? Does this make sense? We'll just stop there. But this would be what? Type 2. And type 2 is, dA is dx dy now. And our cheer is left to right, then bottom to top. So does it mean that a type 1 always is one integral and a type 2 is always split up? No, it's just the situation, right? Whatever your situation is, you just have to do every problem individually and you see what your situation is. It just happened that in this region, the bottom was always the same and the top was always the same. So when we did a type 1, we just were able to do it in one integral. And for this region, the right side was split up into 3 different right sides that caused us to, in the type 2 integral to have to split it up. Okay. Ask if you have a question or if I lost you. Does it make sense? So let's do another example. So I want you to set this one up both ways. Type 1 and type 2. Can I erase? Okay, so here I've got, this is y equals ln of x. And this is y equals 1, and y equals 0, and x equals 0. So first what I want you to do is I want you to sketch that region. Could you sketch that region in R3? Oh, and so here's our function. That's the function, which is the surface. It's like a exponential cylinder, right? Exponential cylinder. So can you sketch that region in R3 first of all, and then can you set up both a type 1 and type 2 integral to find the volume beneath that surface to the xy plane, defined laterally by the region? What's this? Oh, no, no. So is the type 1 0 to 1, 0 to e? Is that right? Christian says no. Why not?
Don't you have to get the first region? So it'd be 0 to 1 and then you have to break it the second region.
Yeah, so 0 to 1, 0 to e only gets you this much.
You have to
Add what? So the bottom. So when you go bottom to top, your bottom is split up. You have a 0 bottom, and then you have ln of x at the bottom, depending on what y is. So then we'll have x, or bottom will be ln of x to 1. That's when x goes from 1 to e.
the first one 0 to 1.
0 to 1, 0 to 1. Thank you. That's right. And then this time the type 2, you can do it in one integral, because you go left to right. You go 0 to ln of x, which is x equals e to the y, and then from 0 to 1. So in this case, the type 2 is one integral, and the type 1 had to be split up because the bottom was split up. The bottom is split between y equals 0 and y equals ln of x. Okay, I'll stick around if you have questions about that. Shane, are you good? Yeah.
Why did you split the second one?
Because left to right, you got left, the whole left side is the same, and the whole right side is the same. So you don't need to split it up. Because for every y value, you have the same left side and right side.
Oh.
You see that?
Oh.
The left side here is all the same, and the right side is all the same.
Okay.
So any strip would be always from 0 to the curve.
Okay. Oh, okay.
Yeah.
Thank you.
But this way, you have to split it up because the bottom is different.
Right.
Going up.
Right, right, right.
Yeah.
Okay. Makes sense. All right. Thank you.
Yep.